So far, you learnt about the theories of acids and bases, their relative strengths, and conjugate acid-base pairs. This lesson deals with pH, indicators, and how they work. Long ago, people found out that acids affected on some plant-based dyes. Litmus was one of the first substances that was noticed to show color changes when it was put into acid and bases. Litmus is an example of an indicator. An indicator is a substance that indicates the degree of acidity or basicity of a solution through characteristic color changes. The pH scale ranges from below 0 to just above 14. pH equals 7 is called the neutral point. All values below 7 show that the solution is acidic. All values above 7 show that the solution is an alkali or basic solution. Universal indicator gives a range of colors for different values of pH. Using universal indicator enables a closer approximation of the pH value of the solution. Universal indicator consists of thionyl blue, methyl red, bromothymol blue, and phenolphthalein mixed together in the form of a solution. This mixture is important because each component has specific color changes that occur at different pH values. Their combination of colors produces the gradual color changes shown in the indicator chart. The three indicators that we use in school laboratories when we study acids and bases are methyl orange, bromothymol blue, phenolphthalein. The table shows the color changes and the pH at which the color change occurs. Methyl orange changes color at pH equals 3,7. Note that this change happens when the solution is acidic. Methyl orange discriminates between a strong acid and a weaker acid. As the solution approaches its color change range, it turns orange, a mixture of red and yellow. Over the range, 3.1 to 4.4 methyl orange is orange. It is a red color at pH below 3.1 and its yellow color above pH 4.4. Phenolphthalein changes color at pH equals 9.3. A pH change to show the difference between a weak and a strong base. As the solution approaches its color change, it may show quick flashes of purple followed by a return to a colorless solution. A mixture of colorless and purple. In solutions of more than pH 10.0, phenolphthalein is purple. Litmus is red in acid and blue in base. The color change occurs at the neutral point pH equals 7. How does the color change occur? Think about this idea. Indicators measure the concentration of hydronium ions in solution. Indicators must be undergoing an acidic base reaction themselves to be able to do this. Let's represent the indicator as HIN, where H plus is the proton that it can donate, and IN as its anion. HIN dissociates in water to produce the proton and its anion. These reactions are in equilibrium. The indicator dissociates and it recombines to form its molecular form at the same rate. Indicators change color in acids and bases. Litmus is red in an acid and blue in a base. Its molecules, HIN, and anions, In-, have these particular colors, red and blue. Let's work out which of HIN and In- is red for litmus. Litmus is red in an acid. The equilibrium of the litmus indicator responds to the change in external conditions. The concentration of hydronium ions increases when litmus is dropped into an acid. Applying Le Chatelier's principle shows us that the reverse reaction is favored in the presence of an acid. The system is exposed to an increase in the concentration of hydronium ions. It will respond by favoring the reaction that reduces the hydronium ion concentration. The equilibrium shifts to produce more litmus molecules. The color changes to red. Litmus molecules are red. Let's review the situation by placing the indicator litmus in an alkali. There are very few hydronium ions in solution in an alkali. There are many hydroxide ions. The hydronium ions that litmus produces join up with hydroxide ions to form water. The litmus equilibrium is upset because the hydronium ion concentration decreases in an alkali. The forward reaction that produces hydronium ions is favored. The color changes to blue. In- anions of litmus are blue. Methyl orange is red in a strong acid and yellow when the pH is above 3.7. What color are the molecules of methyl orange in a strong acid? And what is the color of their ions? A high concentration of hydronium ions favors the formation of molecules, and the color changes to red. The molecules are red. A lower concentration of hydronium ions favors the production of ions, and the color changes to yellow. The ions are yellow in color. Fascinating stuff. I'll leave it to you to explain why bromothermal blue is green at pH equals 7. How does the pH scale work? And why is pH equals 7 considered to be the neutral point? Surely, chemists could have chosen 0 as the neutral point. Pure water is neutral. It is neither acidic nor basic. Yet we have discovered that water can act as an acid and a base during reactions. Water manages to do this by ionizing to a small extent. The ionization equation of water shows that two molecules of water form hydronium and hydroxide ions. This reaction occurs spontaneously. This equilibrium system always exists in water. Writing an equilibrium constant for the reaction, we see that the denominator is equal to 1 since there is no value that we can assign to the concentration of pure liquids, water in this case. Removing the denominator, we find that Kc is equal to the product of the hydronium and hydroxide ion concentrations. The equilibrium constant for water is named the ionic product of water. We use the symbol Kw for this expression. Its value at 25 degrees Celsius is 1 times 10 to the power of minus 14. One times 10 to the negative 14 is a very small number. It is 13 zeros after the decimal comma followed by 1. Yes, it tells us that very few water molecules ionize at 25 degrees Celsius. How many actually ionize? From the equation for the equilibrium system, we see that two molecules of water produce one hydronium ion and one hydroxide ion. The number of hydronium ions in solution is equal to the number of hydroxide ions. Their concentrations will also be equal. Let the concentration of hydronium ions be X. The concentration of hydroxide ions is also X. The ionic product Kw becomes X times X, or X squared equals 1 times 10 to the negative 14. We are looking for the value of X. Take the square root of X squared and its value. X is equal to 1 times 10 to the negative 7. X equals 0,6 zeros and then 1. 1 molecule in 10 million water molecules ionizes at 25 degrees Celsius. One molecule in 10 million releases a proton in water. No wonder we find that water does not taste sour or soapy. It tastes neutral. It is neutral. It has pH equals 7. Why is its pH equal to 7? pH is defined as the negative log to the base 10 of the hydronium ion concentration. That's its official definition. Remember that it measures the concentration of hydronium ions in solution. Well, that's how it measures them, and the negative log to the base 10 of the hydronium ion concentration. Applying the definition of pH to water at 25 degrees Celsius, we know that the hydronium ion concentration is 1 times 10 to the negative 7 mole per cubic decimeter. pH of water equals the negative log base 10 of 1 times 10 to the negative 7. Using the calculator, we find log base 10 of 1 times 10 to the negative 7 is equal to 7. The pH of pure water at 25 degrees Celsius is 7. The neutral point of the pH scale is therefore 7. Calculations of pH is limited to strong acids and strong bases only for grade 12 metric exams. This is relatively good news. We assume complete ionization of any strong acid or base when we calculate pH. Let's try a calculation for 0,2 mole per cubic decimeter. Hydrochloric acid. Hydrochloric acid is a strong acid. It ionizes completely in water. Writing the ionization equation, we see that the same number of moles of hydronium ions form for each mole of hydrogen chloride gas. The concentration of hydrogen chloride gas is 0,2 mole per cubic decimeter. Therefore, the concentration of hydronium ions in solution is 0,2 mole per cubic decimeter. pH equals negative log to the base 10 of the hydronium ion concentration equals negative log to the base 10 of 0,2 mole per cubic decimeter. Use your calculator to find the answer. Equals minus 0,70 equals 0,7. This answer makes sense. It shows us that hydrochloric acid of a concentration of 0,2 mole per cubic decimeter has a pH of 0,7. We expect the pH to be low because hydrochloric acid is a strong acid. Let's calculate the pH of a strong alkali. Remember that the ionization constant of water at 25 degrees Celsius is equal to 1 times 10 to the minus 14. Strong alkalis are sodium hydroxide, potassium hydroxide, and lithium hydroxide. These alkalis release hydroxide ions into solutions, as can be seen by their dissociation equations. This affects the ionization of water by favoring the formation of water molecules, shifting the equilibrium system to the left. Calculate the pH of a 0,5 mole per cubic decimeter solution of sodium hydroxide. Sodium hydroxide dissociates into its ions. A hydroxide ion is released for every sodium hydroxide particle. The concentration of sodium hydroxide is 0,5 mole per cubic decimeter. The concentration of sodium hydroxide ions in solution is 0,5 mole per cubic decimeter. We need to find the concentration of hydronium ions in solution. The concentration of hydronium ions times the concentration of hydroxide ions equals 1 times 10 to the negative 14. Substitute the value of 0,5 mole per cubic decimeter into the hydroxide ion concentration. Now determine the concentration of hydronium ions by rearranging the values. The concentration of hydronium ions is 2 times 10 to the negative 14. Now calculate the pH. pH equals negative log to the base 10 of the hydronium ion concentration, equals negative log to the base 10 of 2 times 10 to the negative 14, equals 13,7. Pretty neat. The pH of sodium hydroxide should be close to 14, and there it is. One last thing to look at in relation to indicators and pH is to measure the pH as equal volumes of acid are added to a base during a neutralization reaction. Start with a measured quantity of base. Here we choose to use 50 milliliters of sodium hydroxide. Bromothymol blue is chosen as the indicator for this investigation. It is blue in the base. Use a pH probe to measure the pH of the solution at the start and each time acid is added to it. Add 5 milliliters of hydrochloric acid to the base. Use the pH probe to stir the contents gently. Take the pH reading. Note the color of the indicator. Repeat this step 15 times. The table and the graph of pH show the results. We refer to this type of graph as a pH curve. It shows the relationship between pH and volume of acid added to the base. Firstly, you can see that the pH started out as being high. The base has a high pH. It remained high for quite a while before suddenly falling to a low value. The color change of the indicator occurred simultaneously with the sudden change of pH. The pH changed rapidly when the neutralization reaction was complete. pH curves can be used to find the approximate pH of the contents at neutralization. In this reaction, we see that halfway pH is about pH equals 7. We are ready to move on now to study neutralization in detail. Join us in the next lesson.